Good morning, physical science students. Mr. Lambert here. Welcome to Lesson 7, Chapter 2, all about motion. I posted a topic in Google Classroom called Lesson 7, Chapter 2, and this video will be found in there as well as the text that I've already put into that topic. I'm going to be pausing this video from time to time just to make sure I have covered everything that we need to cover for this Monday video. It's about motion. So we're changing topics. We're going back to chapter 2. We're going to be studying physics, getting away from chemistry for a little bit. So what is motion? As most of you would probably describe, anything that's moving, right? But you don't have to see something moving to know that motion has occurred. So your textbook describes it. By the way, pages 44 to 50 is this particular section. So I want to make sure I'm hitting everything so that you can complete your assignment that'll get pushed out tomorrow, March 31st. Anyway, you don't have to see something move to know that motion has occurred. So your textbook on page 44 describes motion as a change in an object's position, a change in a position relative to a reference point. For example, if you see a car parked in a parking lot and you close your eyes for a minute and that car goes away, you know that when you open your eyes, that car's not there. You didn't see it move, but motion did occur. We couldn't calculate how fast it was going because we don't have all the information, but we know that motion occurred. So you're going to see that motion is a change in position. There are also two vocabulary words used on page 45 that deal with a change in position, and that is distance and displacement. Once again, distance and displacement. Distance is simply how far an object has traveled from its original starting position. Displacement, however, is a little bit different, and I'm going to move to the whiteboard here to show you. Okay, let's say we have an object who's starting, or an object that is going to go in motion, and they're starting right at the center of this whiteboard here. That's the starting point. Let's say the object travels 10 meters to the right, or 10 meters, we're going to call it east. So I'm going to put a little arrow here, and we're going to write 10 meters. Don't forget, this is physical science, so you're going to see meters, centimeters, kilometers. You're not going to see inches, feet, yards as much. Okay, so this object right now, from its original starting point, has a displacement of 10 meters to the east and a total distance traveled of 10 meters. But what if this object wants to go back in the other direction, the way that it came from? If it starts to go back and it goes back 10 meters to its original location, then you can say that the total, listen to these words, total displacement is 0. It's back to its original spot. However, the total distance traveled, you add them up, that's 20 meters. So there's a difference between displacement, how far away the object is from its original spot, and the entire distance that it traveled. Okay, and then on page 46 in your text, a new topic, a new vocabulary term is introduced, and that is speed. Speed in your textbook is simply defined as a unit of distance divided by a unit of time. I'm reading directly from the book here. Speed is the distance an object travels per unit of time. There is an equation that we use, a mathematical equation that we use to calculate an object's average speed. How fast did it go on average for the entire duration of that trip? So you're going to see this in the future in your textbook and on assignments that will be pushed out to you. Speed equals, I'm going to move my niece here. Speed equals distance divided by time. We can use letters, we can use variables to crush this up a little bit and condense it so we don't have to write the words every single time. Something's average speed, we use for speed, we use S. S, this is what you'll see in the book. S equals D divided by T. Speed equals distance divided by time. Now, I'm going to erase this part up here. I'm going to do the whole thing, actually. Units. What are we going to use for units? Well, since we said that speed equals distance divided by time, think about distance. I mentioned it just a couple minutes ago with that distance and displacement piece. We're going to use, because it's a unit of length, and we're using the metric system, I'm going to use meters because that's the base unit for an average object traveling. So uh, meters is going to be our unit of distance. Time, our SI, our standard unit of time, is going to be the second. So what you're going to see for a standard unit of speed, you're going to see this: meters divided by seconds. Once again, distance over time, meters over seconds. So the standard unit that you're going to see a lot of when we're talking about motion is m/s, or m over s. It doesn't matter. It's distance divided by time. Okay, quick example problem to use that equation. This is from page 47 in the textbook. Here is the problem. It's called calculate speed. A car traveling at a constant speed covers a distance of 750 meters. 750 meters. That right there is a clue that this measurement is the distance that the car has traveled. Once again, the car travels 750 meters in 25 seconds. It says in the problem 25s. What is this? Because of the seconds, that's going to mean, hey, that's the time that it took. What have they given you in this problem? They've given you the distance and they've given you the time. Since average speed equals distance over time, we're simply going to divide the two. Distance, 750 meters, divided by time, 25 seconds. 750 divided by 25. I'm cheating here because it's right in the book. The answer is going to be 30. But 30 what? The speed is going to equal 30. Remember that unit. It's going to involve both of these. It's going to divide them. Meters slash seconds. 30 meters per second. That car traveled 30 meters for every second of the entire trip. So when you're calculating motion, keep in mind meters per second is going to be the most common unit that you'll see. But if you're talking about an object that's moving much, much faster, like a car, we're probably not going to use meters per second. We might use something like kilometers per hour, km/h or hr. But keep in mind, it's still going to be a unit of distance divided by a unit of time. On page 48 of the textbook, the text talks about different types of speed. What I just showed you on the whiteboard, S equals D over T, that is calculating, or the equation to calculate something average speed. But you all know that when you take a trip, think about taking a trip in a car, you're not always going at a constant speed. Sometimes you have to stop at a stop sign. Sometimes you're on a highway and you're going much faster. So your speed is changing. There are other vocab words that are used to describe these changes in speed or these changes in motion. One of them is constant speed. Constant speed is when you are taking a particular trip, when an object is going from its original spot someplace else and its speed is the same for the entire duration of the trip. That is not normally the case in the everyday world. If I were taking a trip to Conval from my house, there's no way that I could go at a constant speed that entire trip. But we could calculate my average speed, total distance traveled from my house to Conval divided by the time that it took. We could calculate it in kilometers per hour. We could do meters per second, miles per minute, but it's always unit of distance over a unit of time. Oh, I have to show you my new shirt. I hope you appreciate that. You know that I like to hike, so that's the way I am social distancing myself. There's another type of speed that's talked about, and that is instantaneous speed. For example, if you're in a car and you look down at the speedometer, the speed that you're going at that particular moment would be something called instantaneous speed. It's not going to be the speed that you maintain throughout the entire trip. It's just the speed at that particular point in time. Okay, this is what motion looks like with a picture version on a graph. Notice I have a distance time graph drawn. We have time with our units on the x-axis. That's where time is always going to be. So as time is going by, these particular objects are covering a distance. I have Natalie, my oldest daughter, Mia, my younger daughter, and Bailey, my dog. These three objects are running, let's say. They're covering a distance in meters over a particular amount of time. You'll have to forgive the messiness. I tried to do this quickly, but to have it make sense. It's got a title, it's got all the labels that we need. And what's it showing? Well, it's showing that they're all running for approximately, it's not perfect, but approximately 30 seconds. But let's look at each particular object. Natalie, she covered well over 500 meters. She went over 500 meters in the 30 seconds that she traveled. And notice the line. My line's not perfect, but it's somewhat straight, somewhat. I was trying to show constant speed, okay? Mia, same thing. She does not cover as much distance. What is she at? Between 400 and 500 meters covered in her 30 seconds. But she also has a relatively straight diagonal line on the graph. That is also showing constant speed. Look what I did with Bailey here, Bailey the dog. She started out with basically a constant speed. She was going the slowest, but then look what she did. Notice how the line sort of flattens out here. I tried to do as best I could. When you have a straight horizontal line on a distance time graph, think about what's happening. Bailey is not covering any distance as time is going by. So that, and I'm trying to represent the fact that Bailey here, she has stopped moving. There is no motion with a straight line, a horizontal line on a distance time graph. Then she picks up her speed again. Whoops, I erased it. And she finishes after her 30 seconds. But that'll give you a good idea on how to calculate average speed, how we look at distance time graphs, and it's going to serve as a good foundation as we move forward and get into more complex concepts like velocity and acceleration.